Now 25 is slightly different. 25 is an endothermic reaction. This is the first endothermic reaction question that we're doing, I think. But anyway, what it's trying to say here is for every mole of ammonium nitrate that is dissolved in a solution, 25 kilojoules of energy will be absorbed. And you need to, so a student dissolve this many grams of ammonium nitrate. So this is essentially, why is it that I can't, oh, maybe it will happen eventually. There you go. Mass of ammonium nitrate is 12.2 grams. You dissolve it in 85 ml of water. I think the assumption that you're going to have to make here is that the volume of the water doesn't change. Okay, at an initial temperature of 28.3. So temperature initial is 28.3 Celsius degree. You need to find the final temperature of the water. So this is somewhat of an opposite process. The first thing we're going to do is we have to work out how much energy this dissolving process is going to absorb, and it has to absorb that energy from the water. So I'm going to start by finding E absorbed by reaction actually. And this can very well happen. You don't necessarily have a exothermic reaction all the time. Energy absorbed by reaction. Okay, the ratio that I have from the thermochemical equation is 25 kilojoules for every 1 mole. So I'm going to convert the mass of ammonium nitrate given to me, which is 12.2 grams, into the number of moles. So I could actually make a comparison with the ratio. So it's just mass divided by molar mass, which is 12.2 divided by something, 48 plus 4. So I got 80 to be the molar mass of ammonium nitrate. So we go 12.2 divided by 80. That is 0.1525 mole. So essentially what I need to find is energy absorbed when 0.1525 mole of ammonium nitrate is dissolved, which should be equivalent to 25 kilojoules being absorbed for every 1 mole based on the thermochemical equation. So if we just rearrange, E absorbed is 0.1525 times 25 over 1, which is 3.8125 kilojoules. So this much energy is going to be absorbed from the water, which means that E released by water is at least has to be the same. So 3.8125 kilojoules as well. So instead of working out, well, you still have to work out the change in temperature, but instead of increasing the temperature of water, this particular case, the temperature of the water is going to decrease, but I still need to find delta T. Specific heat capacity of water allows you to describe and determine any value relating to a change in temperature of liquid water. So it doesn't necessarily have to be an increase. So you can use it for decrease as well. I'm going to rearrange the equation. Delta T is going to equal to E over mc. Now I need a few things. I still need, so first of all, specific heat capacity of water is 4.18 joules. So I need to convert this to joules before I can use it with the specific heat capacity of water. And the second thing is I need to convert the volume, which is 85 milliliter, into grams, into mass, before I can use this. Okay, so once again, I'm going to use the density of water listed in the new data book. And according to that, this is the same as 0.997 grams per 1 mil. So the mass is going to be 85 times 0.997 over 1, which is something I really want to fit this something into one page, so let's try that. 84.745 mil. Oh, sorry, not mil, grams. So now I can sub it in here, and delta T is going to be 3.8125 times 10 to the 3 divided by 84.745 grams multiplied with 4.18 joules per grams per Celsius degree. So the change in temperature, let me just do this on the calculator, divided by 84 and then divided by 4.18, so I get 10.76 Celsius degree, which means that the final temperature is going to be 28.3 minus 10.76 because you have to have a decrease in temperature. So 28.3, 17, we're going 17.5 Celsius degree. So this is the final answer for this question. Okay.